Okay, so there were 3 problems in the written part. Hopefully, the computational part was okay. For the theoretical part, thank you. There were sort of 2 questions that hopefully there were no problems with them. And then there was 1 question that was tricky. So let's just go through it, okay? So question 1 was to show that the ribs complex, so this is such that the diameters is less than alpha, and that the check complex these intersections over x and sigma of b alpha x is not empty, so that these guys are actually simplicial complexes. Right, so the goal with this question was to just remind ourselves what the definitions were, and just to check for once and for all that they were actual simplicial complexes. So what do you have to check? That's the first step when proving things in math. You have to figure out what it is that you have to prove, right? So here in a thought bubble. So remember that K is a simplicial complex if whenever I give you an element of K and I give you a face of sigma, then tau is also in K, right? So it's closed undertaking subsets, non-empty subsets. So let's do it for this guy. So we're gonna let sigma in R alpha, and we're gonna let tau be a subset of sigma that is non-empty. So what we have to show that tau is in here. And for that, we just use the definitions. So if sigma is in the Rips complex, that means that its diameter is less than alpha. Okay, that's what we're given. Now, if tau is a subset of sigma, then its diameter has to be bounded from above by the diameter of sigma. And the diameter of tau is less than or equal to the diameter of sigma, and this is less than alpha, and then this implies that tau is in the Rips complex, which check, simplicial complex. Okay. Now, for the check, yeah.
Do we also need to say tau is the subset?
Yes, we would need to say do that, but tau is a subset of sigma, and sigma is a subset of x, so we're good. Okay. So now let's do the other one. Let's take a sigma in the check complex. And as before, we're going to take a tau which is non-empty, which is a subset of sigma. So this implies that the intersection of the ball centered at x is non-empty, right? Now, if you take the intersection of balls, let's say of points z in tau, right? So here you're intersecting over a smaller subset than sigma. So in particular, this is a bigger set than this. okay? And since this was non-empty by assumption, then this is also non-empty. And that implies that tau is in check. Done. Okay, so that was 1A, just to get ourselves, just to get the blood flowing. Now 1B, and here's where we had the typo. And hopefully we proved the right thing in the homework. So 1B was to prove that we have these continence relations. So what we're going to do is we're going to take. So let's do the first. Let's do this first. So we take something here. That means that, and perhaps we're going to write it as, x0, x1 all the way up to xn. So if sigma is in here, then that means that the diameter of sigma is less than alpha, right? So in particular, the distance from, let's say, x0 to x1 and x0 to xj is less than alpha for all j. Is that cool? Okay. Because the diameter is the maximum of all the pairwise distances between all the elements of sigma. So in particular, if you take the first one and compare it to all the others, then its distance is also less than alpha. Then this implies that x0 is in fact in the ball of radius alpha centered at xj for all j. And that in turn implies that the intersection of the balls is not empty, because you found an element that is in everybody. And that implies that sigma is in the check complex. So we've shown that every sigma in the RIPS is also in check. Okay, okay, so if it is not clear, this is the moment to ask questions. Okay. And then for number 2, so here, for number 2, I guess 2 like this. So let's take an element in the check and try to say that it's in RIPS. So again, take sigma in check, right? And again, this means that the intersection of all the balls centered at points in sigma is not empty. That means that we can find some element y in the intersection. That means that that the distance from x to y is less than alpha for all x and sigma. Okay? In other words, if you let x and x prime be elements of sigma, then by triangular inequality, by triangular inequality, we have that the distance between x and x prime is less than or equal to the distance between x and y plus the distance between y and x prime, and that is less than 2 alpha. Because this is less than alpha, and this is less than alpha. And that implies that the diameter of sigma is less than 2 alpha. And sigma is in the ribs to alpha x. Right? So if you're not used to writing proofs and thinking in this fashion, then it is very, very useful to just do these exercises and write them down very carefully. You know, slowly, there's no rush. Try to write every step so that it makes sense to you. My suggestion is always start with the definitions. Figure out what are the elements, what are the objects that you're working with. Put that at the top. At the bottom, put what it is that you want to prove. And then by sort of rewarding what you wrote, hopefully you can sort of meet in the middle between where you started and where you want to end. Yeah, I know that it's not very sort of technical and careful advice, but so it's something to have in mind. The second question was this thing about the covering radius. And half the battle was to understand what the heck is the bounding radius. I think that's what we called it. Is that what we called it? Bounding radius? Enclosing radius? Yeah, that sounds right. So what is the idea? So you have your ambient metric space M, and you have a collection of points, you know, maybe like that. And these guys are sigma. So you're looking for the for a ball that contains all of these guys. So perhaps you put a center in here, and you draw a ball that contains them. And you're like, okay, great. That is a ball that contains the points. It's actually closed because we have less than or equal to in the definition. And then the radius of this ball is going to be, well, this quantity, whatever that is. And what the covering radius is the radius of the smallest ball that encompasses all the points. In other words, if you put another point, let's say it here, then perhaps you can do better and get a smaller radius. So given sigma in M finite, its covering radius is the smallest alpha for which there is yep. Oh yeah. There is some point in M. This is the center, M sigma, with the distance between x and M sigma being less than or equal to L alpha for all x and sigma. So that's what the definition was. Just half the battle was to just understand that. And then what we have to prove is that that now if you take a data set, so for finite set, then sigma is in the check complex at alpha if and only if the covering radius of sigma is less than alpha. Okay, so there are two directions we have to check. Let's say that we are going in that direction. So we're going to let sigma be in here. So somehow, some way, we have to show that the covering radius is less than alpha, right? So hopefully, with some work, we get to then alpha sigma is less than alpha. And let's just see what this definition gives us. So this means that the intersection of all the balls centered at points in sigma of radius b alpha is non-empty. And what does that mean? It means that there is at least a point. In the intersection, right? So that means that the distance between x and y is less than alpha for all x in sigma. And as before, we get that sigma then is contained in the ball of radius alpha around y. Okay, so what's happening? Let's do it over. We haven't finished it yet. I just want to make a comment. Okay, so here, let's say 0, and say that here is alpha. Okay? Then when you take a point x in sigma, then its distance to y, to this y that we found, is less than alpha, right? So for x in sigma, maybe it's the distance is here. Let's put it over here. Okay? And if you look at all the distances, then they fall somewhere here. And you never actually reach alpha because all the inequalities are strict, and there is finitely many points in sigma. Okay? So, I mean, it could happen that if sigma was infinite, then you could get as close as you wanted to alpha in distances. But since sigma is finite, there is some sort of hard threshold where you cannot move forward. So maybe this is like some alpha minus delta, where this is the delta gap that I'm leaving myself. Okay? So in particular, I can, instead of saying that it is in the ball of radius alpha, I'm going to say that it's in the ball of radius alpha minus delta. And you see why in a moment. I'm going to give myself some wiggle room. So what this implies is that my covering radius is less than or equal to this radius that I have here, because this is the smallest that does something. And then this is certainly less than alpha. I just didn't want accidentally to get alpha sigma to be equal to alpha. I wanted to get the inequality to be strict, which is what we wanted at the end. Okay. Again, if sigma was, for some reason infinite, you could have gotten as close as you wanted to alpha, in which case the actual covering radius would have been alpha. So that's just a little bit of care. Okay, let's go the other way. So, is there a question? Okay. So, for the other direction, then we just give ourselves the condition that the covering radius is less than alpha. Okay. So again, that means that the distance between m, sigma, and x is less than alpha for all x in sigma and some center m sigma. Then, right, because the distance is less than or equal to this guy, right? Sorry, the distance from here to here is less than or equal to alpha sigma, and that is strictly smaller than alpha. So, right? And then this implies, in turn, that m sigma is of all the balls. And that means that the balls, that this intersection is non-empty. Which in turn implies that sigma is in the check complex. Okay? So that's it. Those were points 1A, 1B, and 2. Hopefully everybody did something similar. I want to now rant for a couple of minutes. I like question 2 because it gives us a sort of algorithmic condition for a simplex to be in the check complex, correct? So if you wanted to build this guy algorithmically, what do we have to check? We have to check that the covering radius is less than the alpha, okay? So if you really wanted to compute the check complex. So let me start. In the following sort of super, super easy setting. So this is going to be a remark. So suppose that your data is in fact in Euclidean space, like many of the data sets we deal with. Okay, so what we know is that, so this is the data. So what we know is that sigma is in the check complex if and only if the covering radius is less than alpha. Computing alpha sigma, and perhaps the center, has a name that is called the minimal enclosing ball problem. The minimal enclosing ball problem. Right, so in particular, if you want to build the check complex, you have to figure out what is the covering radius for all the simplices that you could take from X, correct? Can anybody venture a guess of the computational complexity? Like how bad can it be to actually do this? It should be pretty easy, right? It's actually not. There is this algorithm, a Megadose algorithm. And it says that the time complexity is roughly big O of d plus 1. D is the dimension where the data lies, times n. N is the number of data points in X, times d plus 1 factorial. Right? So what it says is that if you fix the dimension, let's say two dimensions, right? So 2 plus 1, 3, 2 plus 1 factorial is 18, right? So 18n. So it's linear in the number of data points, but the constant is this 18, which means that as the dimension in which your data lies grows, this constant is a terrible thing to have. So these guys here, this is okay, this is terrible. As d goes to infinity.
The D has no
Yeah. That's the point. So if you want to construct the check complex, you have to wrestle with this type of time complexity, and that's why it is just not practical to even though we have things like the baby nerve lemma that say that this is a good thing to have, computing it in high dimensions is just not feasible. So that's why you get approximations like the Reeves complex that perhaps have a more difficult theory, but their computation is a bit easier, actually much easier, because you're just comparing diameters. Okay? So that's why I wanted to go through this question. So now we know, so if I were to ask you, implement, so get me code that computes the check complex, then you have to do something that involves computing the covering radius, at least in Euclidean space. And the version that we gave you in the computational activity is only an approximation, right? So otherwise, otherwise it would be a problem. At any rate, that's question 2. Now I want to do question 3. So how many of you were successful in completing question 3? Successful, like you know that is right. Okay, one and 1/4. You didn't sound that sure. What do you guys try? What do you try? Can you remind me your name? Yeah. Auden. Okay. Yeah. Okay. Cycle. Correct. Oh, that sounds fun. Okay. And then try to solve. Okay. I mean, the route of systems of equations is not that crazy, actually. Let me rant for a little bit and say maybe how, by solving system of equations, one can perhaps get to the solution of this problem. Is it Joseph? No. Josh. You're shaking your head violently. It just not? Okay. Okay, so let's try to think about this. Okay, so this was the simplicial complex in question. The vertices were U0, U1, U2, and U0. U0, U1, U2, U0, U3, and U4. Then U3, and U4, U5, U6, U7, and U8. Okay? So 9 vertices. Let's write it here. So number of vertices, 9. Okay, that doesn't sound that bad. How many edges do we have? 27. That sounds worse. And number of triangular faces, 18. Cool. What is the Euler characteristic, by the way? Zero. What are the Betty numbers of the torus? 1, 2, 1. 1, 2, 1. Okay. Okay, cool. So what are we asking? We're asking, so given a cycle, so first of all, let's orient the edges according to the typical order that we use. So 4 like that, 2 to 6. All of these guys go down like this, and all of these go to the right, down, and then 1 to 8, 2 to 4, 0 to 7, 7 to 6, like that, 3 to 8, which one I'm missing, 2 to 5, 4 to 5, 1 to 3, 3 to 5, and 5 to 6, 3 to 6. Oh, one line. This will be useful in a moment. Okay, step back. Okay, cool. So that's the orientation of the 6 and 8. Oh, thank you. 6 and 8. Okay, yes, we have all the arrows. Okay, so what we're saying is given a cycle, right? We called zeta 1 essentially this cycle going to the right. So it is U0, U1 plus U1, U2 minus U0, U2. So that's this guy. And then we have also sigma 2, which is this guy going down. So U0, U3 plus U3, U4, and then minus U0, U4. So that'll be this guy going down. Okay, cool. So now given this, show that there are integers m1 and m2 in Z such that zeta is homologous to m1 times sigma 1, zeta 1, and m2 plus 2. Again, this means homologous. Do we remember what that means? It means that the difference is a boundary, i.e., so that the difference is a boundary. And what does it mean to be a boundary? It means that there is some 2-chain such that when I compute its boundary, I get this guy. Okay, so I mean, in that sense, it feels like a system of equations. What are the unknowns? The unknowns are psi, m1, and m2. Those are the unknowns. Okay. So another way to think about it is in matrix form, right? So, I mean, we know that we can represent these boundary maps as matrices, and these guys as vectors. So essentially, we're looking at a problem that looks like this. This is the matrix that represents delta 2, and we want to multiply it by the vector that has, say, sigma as a column, and we want that to be equal to the vector that is psi minus m1, the vector that has zeta 1, minus m2, the vector that has zeta 2. Does that make sense? Okay, another way to think about this is if I move this side to the left, then what do I get? I get this matrix, right? Plus m1 times zeta 1 plus m2 zeta 2, and this should be equal to to the thing that is given. Okay. Now, if you use your matrix multiplication wisdom, you will see that this is exactly the same as the following. Take the matrix of delta 2 and augment it by putting zeta 1 here and zeta 2 here. And then multiply that by psi followed by m1, m2, and that has to be equal to zeta. Right? Isn't that how matrix multiplication works? Is you're taking, right, so when you multiply a matrix by a vector like this, what are you doing? You're taking a linear combination of the columns, and the coefficients in the linear combination are the entries of the vector. Yeah? So this is exactly, so the thing that I have here is exactly this. So now I have a problem that looks like, A times X equals B. And I have A, I have B, and the question is, what is X? So one could try to solve this integer system of equations. That's the key. Is that this matrix is an integer matrix, and this zeta is an integer vector, and we want the solution to also be an integer vector. So one has to be careful when solving the system. But essentially what you have to show is that the system indeed has a solution. Okay? So that's one way to go. I haven't tried it, so I don't know how hard it is, but it certainly can be done. So this is one way. It's not the way I prefer, but it is one way. Another way I saw, or that I heard actually, was a little bit more computationally intensive, but used exactly what we learned in the class. So this was the path that one of you guys took. So the suggestion was, okay, let's just pretend that we're going to compute the homology of this complex. Let's pretend. So you get C2 going into C1, going into C0, and then 0. This is delta 1. This is delta 2. And then you have bases on each one of these guys, right? So you have the U's in here. Let me use U1 through U, how many vertices? 9. Through U9, instead of indexing by 0. Here we have taus from 1 to 27. And here we have bases, say sigma, from 1 to 18. Okay? So you set up the problem like that. And what do? So you take the usual thing. You compute your boundary matrix for delta 2, your boundary matrix for delta 1. Let me perhaps just say it for delta 2. So you compute your matrix for delta 2, right? So that goes from here to here. For delta 1, there we go. From here to here. So tau 1 through tau 27, and then U1 through U9. As soon as you see these numbers, you should say, I'm not doing this by hand, right? So it is at this point that you should say, I'm going to code this up in Python or something, okay? So you do that. You code it up. And then you reduce the matrix so that it's in Smith normal form. There are packages for doing that. So you get here sort of some tau tilde. You change your bases. Tau now 27 minus z. And then tau tilde 28 minus z, all the way up to tau 27. And then here you get U1 tilde, sort of a new set of bases, U tilde 27 minus z, And then let's just put it like that. And then here you have your tau 1, not tau, sorry, K1 through K27 minus Z. And here, zeros everywhere else. So you do that. So that gives you a basis for the, and let's call them tildes. It gives you a basis for the kernel, for Z, for Zn, for Z1 in this case. So what do? The same thing we did in class. You replicate whatever row column operations took you here, and in particular, take the column operations and apply them inverted to row operations in delta 2. So you take, so now you take delta 2, and right, delta 2 now with these bases. So zeta 1 tilde through zeta Z tilde, and then the basis here is still sigmas. So sigma 1 through sigma 18. And here's where things get hairy. So you reduce this last matrix. So this is supposed to be delta 2, because remember that the boundaries always map into the cycles. So in particular, they only hit the zetas. So you take this matrix and you reduce it. Right? Boom. And then you get a new basis. So here you get sigmas, tildes, sigma tilde 18 minus B, sigma tilde 19 minus B, sigma tilde 18. And here you get some other guys, call them etas. So eta 1. In fact, I haven't used zeta yet. I was careful to use tildes here. So what you want is that let me use etas. Otherwise, it's going to get confusing. So eta 1 through eta 18b. And here's what you want. You want, and this is where it's hairy, you want that after you're done with the Smith normal form reduction, you want only 2 rows here that are 0, and the basis elements that you want should be zeta 1 and zeta 2. And by zeta 1 and zeta 2, I do mean these zeta 1 and these zeta 2. So it is going to be after a very, very careful set of reductions. What this shows is that when you apply the boundary delta 2, then zeta 1 and zeta 2 don't get hit, right? But any cycle, remember that this is a basis for the cycles, right? Now it's going to be written in terms of zeta 1 and zeta 2 and something that looks like a boundary. That's the intuition. And that's how you find your M1 and M2. I didn't try this again. You had to, I would encourage people to code up. I saw at least one solution doing this. So it has potential to work. But yeah, careful. I'm going to show you what I did. And it uses a little bit of what we learned, and it doesn't use so many computations. So that's why I like the solution a little bit better. So here's what I'm advocating for. So last time on Monday, we learned at least 2 things. We learned that if you compute the number of n simplices, then that is exactly the same thing as the dimension of Bn minus 1 plus the dimension of Zn. And the way to remember that is a rank nullity theorem that one can sort of get from the Smith normal form decomposition. We also learned that the dimension of the cycles is literally the dimension of the boundaries plus the Betti numbers in dimension k, in dimension n. Okay, so those were two things that we used on Monday. So let's see how can we use this information to try to tackle our problem of showing that every cycle can be written in terms of zeta 1 and zeta 2. What I'm going to do is I'm going to do a counting argument. And the counting argument is going to give us no choice but for this statement to be true. So here's how it goes. So we have C2 going into C1, going into C0. And I have the boundary maps. Okay? And let me do it pictorially so that hopefully it makes sense. So this is C2, this is C1, this is C0. Inside of each space, for example, here I have the boundaries and I have the cycles. Correct? In here, I have, so since there is nothing to the left, because there are no higher simplices, I don't have boundary. The boundary is only 0. So what I have in here is the cycles. Okay? And all the cycles now are going to go to 0. That's what being a cycle means. But if you apply now the boundary map to all of C2, that's how you get the boundaries. Correct? And similarly here, since now we're going to 0, C0 is in fact the same as the cycles in dimension 0. And here we have the 0 boundary, which is the image of the entire C1, like so. And the kernel is, of course, the things that go to 0, as before. Okay. What I'm going to do next is I'm going to ask about the dimension of all of the spaces that I highlighted. Okay? So let's start from here. So what is the dimension of C0? No, our example. That should be 9, right? So 9 in here. In C2, the dimension is 18. And in C1, the dimension is 27. Okay? I'm going to try to figure out now what the dimension of B0 has to be, what the dimension of Z1 should be, what the dimension of B1 should be, and what the dimension of Z2 should be. Okay? Does anybody see how to fill out one of those empty slots? Using this information and this information? So here's one thing that we can use. We know that Betti 0, we actually proved this. We proved that H0 actually measures the number of path-connected components in the space, correct? So if the space is connected, what should Betti 0 be? It should be 1, right? So we do know that. We know that Betti 0 of our example is 1. Okay? So let's do it here. So I have the following relation. We have the dimension of Z0 is equal to the dimension of B0 plus Betti 0. C0 and Z0 are equal, so this is 9. Betty 0 is 1, so the dimension of B0 has to be 8, hopefully. Boom. Now, let's see here if now we can do something. Of course we can. Now I have the dimension of this guy and the dimension of its image, right? So rank nullity should be able to tell you what the kernel is. So that's the first relation. So the number of one simplices should be the dimension of B0 plus the dimension of Z0. How many one simplices do we have? We have 27, and we've just calculated B0 to be 8. So these should be 19, maybe? So 19. Here's what I want to do. I want to claim that the dimension of B1 has to be 17. That's what I want to do next. I want to make sure that there are 17 guys in here, and that will force me to have 2 guys in here left over as basis elements. Okay? So in order to compute this, I'm going to use this side. I'm going to use not rank nullity on here. Okay, so now you're going to help me compute the kernel of this map, which is, I guess, what you tried. Or, no, you tried this one, right? The kernel of that. We're gonna do this one, which is actually a little bit easier. Okay, so let's take something in the kernel of this guy. Okay, in the kernel of C2 or of delta 2. Okay, so again, I'm looking for the kernel of delta 2, which is Z2. Okay, so what am I going to do? So I'm going to take an element, a 2 chain, right? So let psi be a 2 chain. So I'm going to write it as a sum of 2 simplices. So this goes, so J goes from 1 to 27 or 18. From 1 to 18 of MJ sigma J. And what are the sigmas? The sigmas are these guys, right? So this is maybe sigma 1, sigma 2, sigma 3, sigma 4, and so on. Until I get to sigma 18 over here. And then what I want is that when I compute the boundary, I get 0. This is what I want. So let me start by fixing by letting M1 be M. Right? So I'm going to fix M1 to be just one variable M. I'm going to forget about the index M. Okay? So I have sort of M worth of this simplex right here. Okay? The next thing I'm going to do is I'm going to orient the simplices. So notice that we have this orientation, for example, 0, 1, 3. So we have these sort of clockwise orientation. The trick to figuring out if it goes clockwise or counterclockwise is by looking at whether or not you have 2 consecutive arrows like this. So that gives you the orientation. If you have 2 consecutive arrows going the other way, like that, then the orientation goes like this. So I'm going to continue the orientation. So this goes like that, and this goes like that. This goes like that, and like this. Okay. So we're going to think now very, very carefully. So we want the boundary to be 0, correct? So if I have m worth of sigma 1, when I compute the boundary of this guy, how many times is this edge going to be represented? It's going to be represented m times, correct? Now, the only way I'm going to get to 0 is if I add something else that kills those m edges, right? So I have to add this guy with multiplicity m, but I have to figure out with what orientation do I want m of this guy or minus m of this guy, right? So let's check. So the orientation goes like that. So I have m going this way, and this is also going this way. So I would like it to go the opposite way. So I want minus m in here. Okay? What does that do? It fixes m2 to be minus m. Let's keep going. Now I'm here. So I have minus m worth going this way. And the only way I'm going to cancel the sort of minus m that I have here is if I put m in here. Otherwise, this edge is going to appear minus m times. So I have to cancel it out with m going the other way. So that forces m3 to be m. And hopefully you can see where I'm going with this. The only way this is going to be a cycle is if I see all the triangles with plus or minus sign, depending on how I want to kill things. Does that make sense? So in the end, it has to be that I just get this. And so on, right? So that means that psi actually has to be just m times some combination of sigmas with plus or minus how many of them are there? 18. Sigma 18. Okay. What is the dimension of the kernel? One. If you're gonna be if psi is gonna be in the kernel, it has to be a multiple of this chain. All the other ones are just multiples of this guy. So you only have 1 degree of freedom. Okay. So this is the kernel. This is the base. This is actually a basis element for the kernel. It's the sum of the two simplices with appropriate signs so that the edges cancel out in the middle. Okay. So now we're ready to compute this guy. So it's going to be 17, right? By rank nullity. So if the kernel is 1 and the entire space is 18, then the image has to be 17. Okay. So what do we have? We have that inside the boundaries, I have to have 17 linearly independent, sort of independent elements over the integers, because that's the dimension that we computed. But the cycles have dimension 19, so I need to have 2 other cycles so that I get the right amount of basis elements for the entire cycle. Here's where we use that line in the homework where I said, you don't need to check that there are relations between zeta 1 and zeta 2. In other words, we know that zeta 1 and zeta 2 are cycles, and the fact that there are no relations between them tells you that they form a basis by adding these other 17 elements. So in summary, if I give you a zeta in zeta 1, a cycle, then we can write it in terms of the basis elements. Two of them we know, zeta 1 and zeta 2. So it's going to be some integer times zeta 1 plus some other integer times zeta 2 plus some combination of the guys that are here. But that gives you a boundary. And that means that phi, that psi is cohomologous, is homologous to M1 zeta 1 plus M2 zeta 2. Check. So, yeah. So it was sort of a counting argument by figuring out how many basis elements I have to have, realizing that zeta 1 and zeta 2 were already independent. There were no relations. And there are also no sort of boundary relations between them. So it means that the other 17 basis elements are going to get you boundaries. And that was the strategy. At any rate, as you saw, there are many ways of attacking this problem. You can go the linear systems route. You can go the Python, reduce the matrices and compute homology, as we saw. And there is this other sort of counting argument that, doesn't need so much computation, but it does require you to understand a little bit of what we've done. Okay. Okay. Okay, 15 minutes. Okay, so let me now show you something. And hopefully the computational activity was reasonable. So essentially you just had to copy and paste from the computational activity. Sort of conscientious copy and paste. Okay. Okay, so now we know a fair amount about homology. And it is time to move on to persistent homology, which is the bigger cousin. So when we look at this image, right, we say, oh, that's a circle, right? What is Betty 0? It's many. It's as many as the number of points that you have, because the space is totally disconnected. You would like Betty 1 to be 1 because of the circle, but there is just no paths connecting the points. So Betty 1 is just 0. There are no loops. There are no cycles. In particular, there are no one simplices. So what you would like to do is use these constructions that we've seen, like the check complex or the Rips complex, to turn your data into something that perhaps has topology to it. So for example, here is the check complex at 3 different scales. And the question that we often ask is, what is the right scale to look at the data? So as we saw before, we can compute homology for those complexes. We actually know how to do that. We have algorithms. For doing this. And let's just do the computation here. So the easy one. So this should be Z, right? There is one loop, dimension 1. This also should be Z. The loop is this. And this should also be Z. The loop is this. Okay, so if you were to compute homology at different scales, you're getting that, in fact, you detect homology everywhere. But I would say that not all homology is created equal, in the sense that it is not the case that this loop, which is this Z, is the same as this Z in here. In fact, when you went from left to right, I guess in here, for example, right? If you look at this loop, when you look at it here, it's actually filled in. So you say that actually the class from here to here disappeared. And the same from here to here. The loop that you had here was closed in this side, right? So what we would like to do is to look at these complexes at all scales and track how the homology features are changing, okay? So that's exactly what it is. Look at all scales and try to track homology in various dimensions. And the idea would be that, the lines represent homology generators, or at least the goal would be to have these lines represent homology generators that persist as you change your parameter value, epsilon or alpha. Okay, that's what we would like. And if things go well, then the sort of collections of bars that we get should mimic what the Betty numbers do for the continuous spaces or the simplicial complexes that we've constructed. So that's where we're going. The question then is actually how to do this. What we'll see is that working with integers is not a good idea, is problematic when trying to track how the homology is changing. So for that, we're going to need, first of all, figure out a way to track, and second of all, figure out what the role of the integers is. So what are we going to do? We're going to use our simplicial maps from the beginning of the course, right? So these are simplicial complexes. This is actually contained in here. This is contained in here. So the inclusion gives you a simplicial map from here to here. And the inclusion from here to here gives you a simplicial map also from here to here. So what we'll do is we'll show that simplicial maps can help you track homology classes. That's the first order of business. And then we'll see how changing the integers for something else would allow you to compute these types of bars. Okay? So that's the goal. I think this is a good time to stop. So next time, we're going to start with simplicial maps, the induced maps in homology, and then we're going to move to field coefficients. So have a good rest of the week, and I'll see you next time.